All right, today's lesson is 2.7, Implicit Differentiation. I do realize that there's still a couple of examples in the last lesson on the chain rule that we have yet to go through. I'm going to save those for the next day, and today just go through 2.7. We'll get through that, and then next day when I cover 2.8, I'll also go back and cover off those last two examples of 2.6. So implicit differentiation is an interesting concept in that it affords us a way to take the derivative of an equation where y is not explicitly isolated, right? So we're accustomed to seeing something like, I don't know, so say something like y is equal to, y is equal to, x cubed plus 3x squared, and we can make this a little bit more complicated. We can, you know, have a sort of denominator there, in which case we would use the quotient rule, or we could, instead of having the denominator there, we could make this composition function. But the point is, whether there is a denominator there or not, y is isolated, and so all we have to do is focus on taking the derivative of the right-hand side. But in a case like, say, example 2.7.1, where you have x squared plus y squared equals 25, this is an equation, certainly, but it's not one where y is explicitly isolated. So what you need to do here is, well, you can isolate y, okay, and that's easy enough. You would subtract x squared from both sides and square root, and then you'd have to deal with the positive and negative roots. Or you could sort of differentiate on the spot, which is what implicit differentiation means, right? Implicit meaning differentiating without explicitly isolating y. Okay, so let's see what we can do here. So finding the derivative of y. So here's what I'm going to do. I'm going to take the derivative of x squared, which is easy enough. Okay, so that'd be 2x. And then I'm going to take the derivative of y squared, which again is easy enough. It's 2y. Okay. Now, it's only 2y if we're taking the derivative of y squared with respect to y. But this specifically states that we want the derivative with respect to x. So here's the thing, like, I don't know how y is defined in terms of x, right? For all I know, maybe in this equation, y is actually equal to, let's say, x squared minus 3x, right? I'm just making that up. Like, I don't know. It could be, y could be equal to x squared minus 3x. It could be equal to something else completely. Now, let's say it was equal to x squared minus 3x. Then this equation that I have here would actually be x squared plus y would now be x squared minus 3x, right? But it's y squared, so that squared equals 25. And so if I actually wanted to take the derivative of y squared, then I would bring the 2 down, right? So it'd be 2 x squared minus 3x, drop the 2 to a 1, but then the chain rule would have me go back in and take the derivative of x squared minus 3x, which is 2x minus 3. Okay, so, but the thing is I don't know what y is. Is it x squared minus 3x? Is it something else? Best thing I could do is actually apply the power rule to the y, so 2y, drop this exponent down to a 1, but then also go inside y and take the derivative of y. Now, since I don't know whether it's x squared minus 3x or something else, the best I could do is to just say, well, dy dx, like whatever y is, I have to take the derivative of it. If y happens to be x squared minus 3x, then I guess my chain rule would say that the derivative of the inner function is 2x minus 3. But since I don't know what it is, best I can do is say times the derivative of y, okay? Equals the derivative of 25, which as everybody knows, the derivative of constant is 0, okay? And so that's what I end up with, right? So I've taken the derivative of each of those three terms. Derivative of the first term is 2x. Derivative of the second term is 2y. And then chain rule would have me go back in and take the derivative of y, right? I mean, really, I did it here as well in terms of x squared. I went 2x times the derivative of x, which is 1. Okay, so I did that, then 2y times the derivative of y, and then 0. Okay, so now what ends up happening is I can actually, well, I could simplify some stuff. I could divide everything by 2, right? So I've got three terms here. I could divide everything by 2, and then I end up with x plus y times dy dx. equals 0 divided by 2 is still 0. And then all I have to do to get dy dx is just isolate dy dx. Okay, so then I have y dy dx is equal to negative x. And then I've got dy dx is equal to negative x over y. Okay, that's it. And so apparently negative x over y is the derivative of x squared plus y squared equals 25. By the way, what does its graph look like? One way that you could figure that out is to isolate y. So you would end up with the positive and negative roots of 25 minus x squared. If you graph both the positive root and the negative root, you'll see something interesting, something round in shape as the graph. Okay, let's move on. Find the equation of the tangent line to the graph of the relation at negative 3, 4. By the way, if you actually sub in x is negative 3 and y is 4, right, you get negative 3 squared plus 4 squared, which in fact is 9 plus 16, which in fact is 25. Okay, so definitely this point here is on the graph of this relation. Okay, so find the equation of the tangent line at that point. Okay, so then dy dx, okay, which is our derivative of the relation, which is also the slope of our tangent line, is equal to negative x over y. Okay, so then that means it's going to be negative 3 over 4, which is equal to 3/4. Okay, so the slope is 3/4, therefore y minus 4 is equal to m x minus negative 3, so that's plus 3. So there's our equation, and then we can simply multiply everything by 4, let's say. Okay, so multiplying each of those three terms by 4, we end up with 3x minus 4y. Right, so here's my 3x, the 4y comes over to the right-hand side. I've got plus 9 minus 16 is minus 7 equals 0. Okay, that's it. Okay, so let's move on to the next page, I guess it would be. And we've got example 2.7.2, 3 examples, and then there's our assignment. So it's a relatively short lesson. So same thing. So if you look at this, we've got an equation where y is not explicitly isolated. Or it's not stated explicitly. How about that, right? We don't have a situation where it's y is equal to blah, 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 blah. Okay, so not only that, though, we have actually two terms with y in it, right? And so even if you wanted to explicitly isolate y, it's difficult to do so because you've got y appearing in two terms. One of them it's cubed, and one of them it's tied with the other variable x. So you can see that maybe you thought in this previous page, maybe you thought, okay, Kong, yeah, thanks for the implicit differentiation technique, but really, why learn something new when you can always just isolate y? Okay, and you could in this case, you could isolate y, but the thing is it's not always convenient to isolate y, as you can see in this first example in 2.7.2. So what do we do? Well, fortunately, we're learning how to implicitly differentiate. Okay, so I'm just going to derive on the spot. I'm going to take the derivative of x cubed, which is 3x squared. I'll take the derivative of y cubed, which is 3y squared, dy dx. Okay. Now, in fact, actually, I'm going to write dy dx right now, but I'm actually going to erase it right away, and I'm just going to write something a little simpler. I have a whole bunch of notation that I can use that's equivalent to dy dx, and I'm going to choose to use y prime. Okay. So again, this is chain rule at work, right? I take the 3, I move it down, it's 3y squared, but then that's just the outer function that I've differentiated. Now you got to go in and differentiate y, right? The reason why you have to differentiate y is because you are looking for the derivative with respect to x. We're not looking for the derivative with respect to y. It's with respect to x. So then I have to also I have to apply chain rule in order to make sure that I'm getting it in terms of x. Okay. So then on the other side, 6xy is actually a product. I'm going to look at this as if it were 6x times y, okay? So then product rule would say take the derivative of the first one, so 6 times the fixed version of the second one, okay? So derivative of 6x times y plus the fixed version of 6x times the derivative of y, which is y prime. Okay, so that's just product rule at work, right? It's the f prime g plus fg prime. Okay, so now what I have is I've got two terms. Okay, so there's one term here that has a y prime in it, and there's another term here that has y prime in it. And so what I'm going to do is put those terms on the same side. So basically I've got 3y squared y prime minus 6x y prime. Okay, and then the other two terms, I'm going to dump them over to the other side. So 6y minus 3x squared. And actually, before I go any further, I noticed that all of the terms are divisible by 3. So I could actually simplify right now. So y squared y prime minus divide this by 3 is 2xy prime is equal to divide by 3 is 2y, divide by 3 is minus x squared. Okay. Now I'm going to factor out a y prime, which leaves me with y squared minus 2x is equal to 2y minus x squared. Right, so since these two terms had y prime, I factor that out, and then now I just divide, right? So now I'll just go y prime is equal to 2y minus x squared divided by y squared minus 2x. Ladies and gentlemen, that is the derivative of this original relation, okay? X cubed plus y cubed equals 6xy, okay? So just as a recap, you basically differentiate each term on the spot. Please make sure to remember to apply product rule here. Um, please also remember to apply a chain rule here and here, okay? Because anytime you are trying to derive or differentiate with respect to x and you're given a y, you have to use chain rule because you're not sure exactly how y is defined in terms of x. Okay, let's move on to the next example here. 3x squared y minus xy squared equals 6. Okay, so again, we've got a product here, so I'll just kind of view it as 3x squared times y. And so I'm going to take the derivative of 3x squared, which is 6x, times the fixed version of y, plus fixed 3x squared times the derivative of y, which is just y prime, minus, okay, careful with the minus here. So minus, I'm going to take the derivative, so this is a product again, so I'm going to take the derivative of x, which is 1, times y squared, plus fix x and take the derivative of y squared, which is 2y times y prime, okay, equals derivative of 6 is 0. Okay, so let's clean this up a bit here. So 6xy plus 3x squared y prime minus y squared, and then minus gets distributed over, so minus 2xy prime. Okay, I've got two terms here that have a y prime in them. So I'll move those to the other side. So I end up with 6xy minus y squared is equal to 2xy y prime minus 3x squared y prime. Okay, so everything is good there. 2xy y prime minus 3x squared y prime. Okay, so then 6xy minus y squared equals, let's factor out the y prime here. So I get 2xy minus 3x squared. And then it's just a matter of dividing now, right? So I'm just going to switch sides here. So y prime is equal to 6xy minus y squared all over 2xy minus 3x squared. Okay. So again, applying product rule, applying chain rule, factoring out the y prime once you've grouped those two terms together, and then isolating y prime. Okay, so we'll do this one more time here. In this case, I'm just going to rewrite these radicals as powers. Okay, now I can take the derivative. So power rule says half comes down times x, drop the exponent by 1, negative half. Use chain rule to take the derivative of x, which is redundant because the derivative of x is just 1. Okay, so we're done with that one. Half comes down, y, negative half. But then this one, because it's y, we have to take the derivative of y itself. And since we don't know how it's defined in terms of x, we just write y prime, which represents the derivative of y with respect to x, okay, equals 0. Certainly we can divide out the halves, so the halves are gone. And so I'm just left with x to the negative half plus y to the negative half y prime equals 0. And then isolating, I get y prime is equal to negative x to the negative half divided by y to the negative half. Okay, so that's just moving this term over to the other side, subtracting that from each side, and then dividing by this term in order to isolate y prime. I can clean this up a little bit, so it'll be negative root y over root x, right? Since the negative exponents moves those terms to the other level. Okay, I just want to make sure here, yeah, that's all we had to do is find the derivative of y with respect to x. And that, ladies and gentlemen, is implicit differentiation. You have the rest of the class to complete this assignment as well as any other assignments that you have outstanding. And have a good rest of the day, and we'll see you tomorrow.